the earlier lecture we have seen the needs for speed in terms of solving the matrix equation Ax equal to b. We have seen that the Cramer's method, Cramer's rule that we have been taught in our school days is really not something that can be scaled to large number of equations because of the number of arithmetic operations it takes to get a solution of the Ax equal to b type of system of linear algebraic equations. Perhaps the best general purpose method for the solution of Ax equal to b is the Gaussian elimination method, and one could call this as the most efficient direct method for the general system Ax equal to b. What we mean by general system here is something that in which A is not specially structured. For example, in some kind of systems maybe you do not have the sparsity that we come to expect with the CFD type of things. We have every element of this is filled. So when you have low sparsity and most of the elements of A are non-zero, then there is no special diagonal structure like what we are seeing here for A. For that kind of general method, general type of system of equations, one would say that Gaussian elimination method is probably the most efficient method, most efficient direct method. There are other direct methods which are much faster, which require far fewer number of arithmetic operations, but in the general case this would be the best thing. And the idea of this particular approach is to convert the coefficient matrix into an upper triangular matrix through a process known as forward elimination and solve the converted equation by back substitution. So that is pictorially shown here. You have a matrix A which has elements along the diagonal and above the diagonal and below the diagonal. All these things are non-zero elements, and through the process of forward elimination we convert this into an upper triangular matrix here, in which you have non-zero coefficients are appearing only in the upper triangular part of it and not in the lower triangular part of it. Below that diagonal, below the central diagonal, all of them are 0. What it means is that each of them, each row here corresponds to an equation, and here you have this a11 x1 plus a12 x2 plus a13 x3, all that equal to b1, and then a21 x1 plus a22 x2 plus a23 x3 and so on up to equal to b2 and so on, like that we have the equations. So in every row we have all the coefficients are coming here, but if you look at this particular thing, all these elements are 0. For example, if you go to the last row here, you will have some coefficient a nn times xn equal to bn, okay, where ann and bn are different from what we originally started with, but still it is an equation which contains only one variable xn. So you go to the last one and then you can solve it directly and say that xn equal to bn by ann. And if you come to the next row here, then it is an equation which contains this non-zero diagonal and this non-zero diagonal. So that is like a n minus 1 a n minus 1 x n minus 1 plus a n minus 1 n x n equal to b n minus 1. So that has two variables x n and x n minus 1, out of which we have already computed x n by solving the last equation, and we substitute that value here and you have now an equation containing only one variable x n minus 1. So you get that directly by solving this. So once you convert this coefficient matrix A containing zeros both above and below into an upper triangular matrix in which all those elements which are below the diagonal matrix are 0, then it is possible to solve this system of equation, which is nothing but a modified way of writing this equation. This system of equation is such that you can start with the last equation, get xn, and then substitute the value in the one above and then that becomes an equation for xn minus 1, and that will be solved, and then you come to the next equation which contains has xn minus 2, xn minus 1, xn as the variables, but by this time you have already evaluated xn and xn minus 1. So, you substitute those values and then solve for xn minus 2. So, you can do back substitution from the bottommost thing and then come up here and then solve for x1. So, you can successively solve for xn, xn minus 1, xn minus 2, xn minus 3 all the way up to x2, x1. So, that is known as a back substitution method. So, you have a forward elimination method where you are converting these non-zero elements into 0 here, and in the process convert the A matrix into an upper triangular matrix, and then substitute this upper triangular matrix, which is a different way of writing this Ax equal to B as A prime x equal to B prime. Okay. So, that is derived from this, and it is just modified through certain multiplications and elimination process, and the resulting equation structure is modified to give you a solution by successive back substitution. So, let us just see how it actually works. You may be familiar with this. You have a set of equations, 4 equations here involving x1, x2, x3, x4. There are 4 equations. So, if you want to eliminate x, you first start by saying that you will eliminate x1 from this equation and this equation, this equation. And how can you do that? If you multiply this equation, the first equation, by 2 and subtract from this, then you would have gotten rid of this x1 from the subtracted equation, and so in the process you will be eliminating from this equation. With the help of the first equation, you will be eliminating x1. Similarly, you come to this equation, the third equation. With the help of the first equation, you can eliminate x1 from this. For example, multiply the first equation by 4 and subtract from this. That will get rid of this 4x1. And similarly, you come back to this and then you multiply this by 3 and then subtract from this. The resulting equation will not have x1. So, in this process, you can, using the first equation, you can eliminate x1 from the second equation, third equation, fourth equation. In the process, what are you doing? You are just multiplying one equation and then subtracting from another equation. All valid operations, as long as it is done equally to both left hand side and right hand side of the equation. You are not changing anything except reordering a bit. So, in the process you can eliminate x1 from the 3 preceding equations. Now, you have one equation involving all the 4 variables and 3 equations involving only 3 variables, x2, x3, x4. You have eliminated the participation of x1 from this. Now, you take the second equation which has x2, x3, x4 and then use that to eliminate x2 from the third equation and the fourth equation. And if you do that, then you get a first equation containing all the 4, second equation containing only 3, x2, x3, x4, and third and fourth equation containing x3 and x4 in both equations. Now, you take the third equation and eliminate x3 from the fourth equation. So, then you have a fourth equation which contains only x4. So, then you have fourth equation containing x4, you solve for x4, and then you come to the modified third equation which has x3 and x4. You use x4, which you substitute x4 and then solve this for x3, and then you come to the modified second equation and then substitute x4 and x3 that you got, solve for x2, and then you come to the first equation, substitute for x2, x3 and x4, and then you get x1. So, that is the process by which we can do this, and that is what is shown here. You take this set of equations. The objective of the forward elimination is to transform the coefficient matrix Aij into an upper triangular array by eliminating some of the unknowns from the equations by algebraic operations. This can be initiated by choosing the first equation as a pivot equation and using it to eliminate, in this case, u1 from each of the subsequent equations, and this is done by multiplying the first equation by a21 by a11 and subtracting it from the second equation. Okay. So, if you multiply this by a21 divided by a11, then obviously this will cancel out and you get a21 u1, subtract it from this, you eliminate this. And then similarly a31 by a11 is what you multiply the first equation by and then subtract from the third equation, and then you can do that. So, if you do this at the end of the first set of elimination of u1 from all these equations, you have the first equation unchanged, the second equation is now with modified coefficients a primes and also the right hand side c prime here, and this set of equations will not contain u1 as a variable. And now you take this set of equations and make use of this as the pivoting equation and eliminate u2 from all these things. And then if you keep on doing this until you have done for all of them, you will end up with the first equation containing all the n variables, second equation containing all variables except u1, third equation containing all the variables except u1 and u2, and so on, n minus 1th equation containing all the equations, all the variables up to except up to n minus 2. So, it has n minus 1 and n minus n here, un here, and then the last equation contains this only this equation. So, now you can solve this for un and then substitute in this, solve for un minus 1, and then you go back here and then solve this for un minus 2 and so on. So, that is the back substitution process. Okay. So, this completes the forward elimination process, by which time you have got this set of equations in each of which one additional variable is missing. So, the back substitution process consists of solving the set of equations by successive substitutions starting from the bottommost equation. Since this equation contains only one variable un, it can be readily calculated as c double prime n divided by a double prime n n, and then you come here and then you can solve it like this. So, this process is repeated until all the variables are obtained. Okay. So, this is the Gaussian elimination process. To summarize, you convert A into an upper triangular matrix by a process of forward elimination, in which you make use of one equation to eliminate that particular variable, one variable from all the subsequent equations, and then you go on with the process until you have eliminated n minus 1 variables from the last equation through a process of this successive forward elimination, and then you get the solution by backward substitution. And this is considered as a very efficient method, which will involve n cube by 3 number of mathematical arithmetic operations of for large values of n. When n is large, that is when the number of unknowns is large, then the number of multiplications and divisions required to do this whole process is about n cube by 3, and n cube by 3 is the number of arithmetic operations that are required to do the forward elimination process. The backward substitution process requires something like n square number of arithmetic operations. Okay. So, the total number of operations is n cube by 3 plus a constant times n square, and as n becomes very large, then n square contribution to the whole sum will be very small. For example, if n is equal to 1000, the first operation will require 10 cube 1000 to the power cubed, so that is 10 to the power 9 by 3, and the second set of operations will involve only of the order of 10,000 square, that is million. So, you can forget the millions when you have the billions, and if n is 10,000, then the first one will have 10 to the power 12 and the second one will have only 10 to the power 8. So, that becomes even more negligible. So, as the number of equations becomes bigger, the time of computation for forward elimination increases, and the backward substitution also increases, but not as much as rapidly as the forward elimination process. Therefore, for large values of n, Gaussian elimination takes number of decimal place number of multiplications and divisions of the order of n cube by 3. And what is n cube by 3? If we go back to the morning example of say, now you say that n is equal to 10,000, 10 to the power 4, then the number of arithmetic operations is 10 to the power 4 cubed, so that is 10 to the power 12. So, even for 10,000 unknowns, 10,000 equations, you require only 10 to the power 12 by 3 arithmetic operations. So, if you have a gigaflop machine or a petaflop machine, you will get the solution in fraction of a second, whereas the Cramer's rule for 30 equations itself, it is taking 10 to the power 33 operations, and Gaussian elimination for 10,000 equations will take of the order of 10 to the power 12 operations, and that is the advantage of the Gaussian elimination method. And this is considered as the most efficient method for the solution of Ax equal to b, when A does not have any specific advantage that we need to that we can exploit, which is not the case in CFD problems, many CFD problems. In many CFD problems you have sparsity as one very characteristic feature. It also plays to the advantage of the Gaussian elimination, because in order to do the elimination process from your set of equations like this to reach up to this eliminated process, in the process of that you would have multiplied these coefficients enormous number of times. If you have 10,000 equations, you would have multiplied this by maybe close to 10,000 number of times. Okay. So, that means that any small errors that you make, rounding off errors, can build up in the process. So, it is important to choose the right kind of coefficients to eliminate, and this is known as pivoting strategies, and I would refer you to standard books of numerical methods to look at the pivoting strategy in case you are doing Gaussian elimination method for the solution of Ax equal to b in the general case. Okay. The build up of round off errors is not such a big problem when you have sparse matrix as we have in CFD, but still it is something that we have to watch out for. We also have to watch out for division by 0 and those type of things, and if you do proper pivoting strategy, then division by 0 will not happen. Now, another important thing about Gaussian elimination process is that it will work provided we have a set of equations which are irreducible and they promise a unique solution, in the sense if determinant of A is not 0, then you can make use of Gaussian elimination method. If you want to get very good accuracy of computation, then you have to use a proper pivoting strategy. Okay. So, that is Gaussian elimination method. We look at one more method which is sometimes used in CFD computations. Gaussian elimination method is not so much used because it does not take advantage of the diagonal structure. Okay. So, here LU decomposition is also something very similar. It also does not take advantage of the in its original form, in its standard form, it does not take advantage of the diagonal structure, but it has certain special features which will make it more attractive than Gaussian elimination method. Now, what is LU decomposition method? Here the coefficient matrix A alone is decomposed into a product of a lower triangular matrix and an upper triangular matrix. So, that is A is written as L times U. This is matrix multiplication, something that we have to keep in mind. So, you have a matrix which has both non-zero components both above the main diagonal and below the main diagonal like this, and this is decomposed into a product of a lower diagonal matrix. So, that is in which all the elements above the diagonal are 0 and only those below the main diagonal are may contain non-zero elements, and so this L times U, which is where U is an upper triangular matrix like this. Okay. So, if we can do this decomposition, then the solution of the resulting LU equal to B is relatively easy. So, with LU decomposition, the matrix equation A phi equal to B is written as L times U times phi equal to B, and this equation is solved in two steps. First we solve for Ly equal to B, okay, and in this equation the unknown is y, because we know L, we have decomposed A into L and U. We will see how it can be done, and then B is already known. So, from this you get y here, and once you get y, you can solve for U phi equal to y, and from this you get phi. Okay. So, suppose you put U phi equal to y in this equation, then that becomes Ly equal to B. So, you first solve for y and then substitute the y here and then solve for U, solve for phi in this. And the advantage of this and this solution is that Ly equal to B is a forward substitution process. So, this in this first equation has only one variable, second equation has two variables, and out of which you have already got one, and then you can get this by substitution, and then you can come to the third equation which has again some three values, and you can continue like that. Okay. So, the solution of Ly equal to B is by forward substitution, it is not by forward elimination, and similarly solution of U phi equal to y is by backward substitution, and that again is not by elimination process, it is by back substitution process. So, this solution of this requires n square number of arithmetic operations, and this requires n square number of arithmetic operations. So, it is the order of twice the number of back substitution process is what is required, which is much less than the n cube by 3 number of mathematical operations that are required for the Gaussian elimination process. Okay. But the catch is, what does it take to decompose A into a product of L and U, and it turns out that that is the really time consuming process, and the process of writing A equal to LU is very similar to the process of Gaussian elimination, so that it will take n cube by 3 number of arithmetic operations just to do this decomposition. So, when you look at it, LU decomposition is not as good as Gaussian elimination, because you have the same number of arithmetic operations which are required to do the decomposition, and after decomposition you have to solve twice this forward or backward substitution process. So, you are solving at least one of these equations more than in the case of Gaussian elimination method. So, in fact, it is slightly more in terms of more demanding in terms of number of arithmetic operations. But if you have a problem in which A phi equal to B is followed by some A psi equal to C and A eta equal to D like that, okay. So, in which you have to solve a number of equations for which A is the same matrix, then you need to do the decomposition only once, and then you can solve this as Lu phi equal to B, and then Lu psi equal to C, and then Lu eta equal to delta. So, in that way you can solve this every time. For the first equation you are taking more number of arithmetic operations than the Gaussian elimination method, but in the second and third equations you are taking only n square number of operations, because you are solving only these and not for L and U. So, if you have a special situation in which you have to solve Ax equal to B and Ay equal to C and Az equal to D and so on like that, then it would make sense to convert A into Lu, so that you can write this as Lux equal to B and LUY equal to C and LUZ equal to D, and solve these things by combination of forward and backward substitution. So, when you do that, then it becomes advantageous. Okay. So, the factorization of A into L and U, there are some specialized methods for this, and we can use those methods for this, and I would refer you to standard books of numerical methods, and they hinge on the fact that this is equal to this times this. Okay. So, this times this plus this times this plus this times this and so on. Similarly, if you take this row A22, it is equal to this row multiplied by this column. So, the corresponding elements M21 U12 plus M22 U22 plus M23 U32 plus M24 U42 is all equal to A22. So, you have that condition. Based on that condition, you can find out M and U elements of the lower and upper triangular matrix in a certain sequence, and that sequence is in the form of Doolittle algorithm, and those type of algorithms are there, which will enable you to solve for elements of L and U in a sequential way, and that decomposition takes n cube by 3 number of arithmetic operations. Okay. So, in that sense, LU decomposition is not any more efficient than Gaussian elimination method when you are solving only one equation Ax equal to B. But if you are solving several equations with the same A, with the same coefficient matrix, then you convert A into LU once and then use that LU decomposed form of the equation to solve subsequent equations. So, when you have this type of approach, then it is possible to come up with an efficient method, and there are other conditions which we will see later on in which this LU decomposition used. For example, through a process known as approximate LU decomposition or incomplete LU decomposition, and these are used to construct better methods, more efficient methods than the pure LU decomposition or Gaussian elimination or even Gauss-Seidel method. So, what we have seen in this lecture are two special efficient methods for the solution of Ax equal to B, and these are two direct methods. The first one is the Gaussian elimination method, the other is the LU decomposition method. When you have banded matrices, when you have diagonal structures, and when you have sparsity, then it is possible to take advantage of the sparsity and the bandedness to come up with a very efficient method, especially for a tridiagonal matrix. So, in the next class, in the next lecture, we will look at the tridiagonal matrix algorithm, which is applicable for the special matrices in which coefficient of matrix, the coefficient matrix here has 3 adjacent diagonals including the main diagonal. So, that is the type of AFI equal to B kind of solution that you have. You have this Ax equal to B type of thing involving only 3 diagonals when you are discretizing for example, d square t by dx square equal to constant. So, if you do that using central differencing, then you get a tridiagonal matrix. So, in case of 1D type of equations involving 1D parabolic type of elliptic type of things, you get a tridiagonal matrix, and when you have the tridiagonal matrix, then we can have an efficient solution method. We have also seen this tridiagonal kind of structures when we are dealing with compressible flow calculations. So, in the next lecture we will look at the tridiagonal matrix algorithm, and then we will see under what conditions it can be applied, and we will look at some other basic methods like the Gauss-Seidel method, which we have already used in the first module, and Jacobi method. Thank you.